All right, testing my mic here. Sounds good enough. Let's switch to my other overlay here. And there we go. So, yep. Welcome back to my stream. I took a long break here for about I think the last time that I streamed was 10 days ago or something like that. And to all those who are wondering, nah, I'm not dead. I'm still alive and kicking. Uh, yep, excited as always. Let's get to it. Continue with what we were learning with Pytorch. All right. So it's been a long time. Let me just see where we left off last time.
Mega taskers are not quick, we are super quick. And that's why we need a phone with a super fast processor, a super cool design, and a super stable camera. The iQOO Z9S fully loaded for mega taskers. Search iQOO Z9S on Amazon right now.
Good morning. Well, might not be morning wherever you are in the world. It's nice and early here. I'm up recording some videos because we have a lot of momentum going with this. But look at this. I took a little break last night. I have a runtime disconnected, but this is just what's going to happen if you're using Google Colab. Since I use Google Colab Pro, completely unnecessary for the course, but I just found it worth it for how much I use Google Colab. I get longer idle timeouts. So that means that my Colab notebook will.
All right. So before we left off, we were trying to make a neural network which could identify between different type of clothing in the fashion amnest. Do you call it database? Data set is what we call it. Um, and now that's where we left off last time. We built out the training and testing loop for that, and we functionized it for lack of a better word. And then, what were we doing? There is a fashion amnest model version 1. For the loss function, we had taken cross entropy loss. For optimizer, we took stochastic gradient descent. Train step, test step. Yep, I remember this. Oh, we also made a model version 2, huh? Which replicates tiny VGG. What is tiny VGG? It's CN explain. That was the side, wasn't it? CN explainer, as they said. Anyhow, so this uses tiny VGG, and we took it. Yeah, it's written plain as daylight over here. CN explainer website. Took it from here. The input layer represents the input image into the CNN because we use RGB three channels, okay, red, green, and blue channels. But we have only two channels, black and white, because we're using a grayscale image. Use the color scale when you click on the convolutional layer. The convolutional layers are the foundation of CNN as they contain the learned kernels, which extract features that not extinguish, distinguish between different images from one another. This is what we want for classification. As you interact with the convolutional layer, you will notice links between the previous layers and the convolutional layer. Each link represents a unique kernel which is used for the convolutional operation to produce the current convolutional neuron's output or activation map. Basically, it's just describing that it learns from each uh, layer, each part of the image as it goes on. Uh, yeah, there's just a lot of technical jargon written over here. And yeah, okay, the convolutional neuron performs the element-wise dot product with a unique kernel for each pixel, right? And the output of the previous layer's corresponding neuron. This will yield as many intermediate results as there are unique kernels. The convolutional neuron is the result of all of the intermediate results summed together with the learned bias. Okay, alright. Hmm. For example, let's look at the first convolutional layer in the tiny VGG architecture above. Notice that there are 10 neurons in this layer, but only 3 neurons in the previous layer. One, two, three, four, five, six, seven, eight, nine, 10. Yeah, right, there are 10 layers here, but only 3 layers, 3 neurons before that. Right. But only 3, yep, yep. In the tiny VCC architecture, convolutional layers are fully connected, meaning each neuron is connected to every other neuron in the previous layer. Alright, okay. Focusing on the output of the topmost convolutional neuron from the first convolutional layer, we see that there are 3 unique kernels when we hover over the activation map. 3 unique kernels. This one, okay. See what that means. Let's just full screen this for a bit. It readjusts itself. Let me just set reload. Slide kernel over input channel to get intermediate result. Focusing on the output of the topmost convolutional neuron from the first convolutional layer, we see that there are 3 unique kernels when we hover over the activation map. So, so what that means is, so this is the first convolutional layer, and this is the activation map, the ReLU map. There are 3 kernels here. What is a kernel? So what is a kernel and CNN? Convolutional kernels, also known as filters, are small matrices used for the convolutional operation. These kernels slide across the input data, performing element-wise multiplication with the corresponding pixels and producing a feature map that highlights specific patterns of features in the input. So kernel is the thing going over each pixel. That's what uh, that's what I understood out of it. Anyway, let's just read through the rest of the article. We see that there are 3 unique kernels when we hover over the activation map. I see a lot more kernels there. Maybe kernel doesn't mean a pixel there. There are 3 unique kernels when we hover over the activation map. Oh, oh, ah, okay, okay. So this is a kernel, this is a kernel, this is a kernel. Oh, so this entire thing is a kernel. Hmm. Anyway, the size of these kernels is a average one second. What's to know here? As you hover over the activation map of the topmost node from the first convolutional layer, you can see that three kernels were applied to yield this activation map. Alright, alright. This entire what's right subimage is a kernel in that case. And the convolutional operation gets take place on each pixel of this kernel is what I understood from that. Yeah. Okay, anyhow, let's just continue. Size of these kernels is a hyperparameter specified by the designers of the network architecture. Okay, in this case, the size is 64 into 64, which, let me see if I can do this in my head. 64 square is 4256, 4256. Is that correct? No, I was wrong. It's 4096. You're right, it's 4096. Anyhow, the dot operation uses a stride of 1, which means that the kernel is shifted over 1 pixel per dot product. But this is a hyperparameter that the network architecture designer, which is us, can design to better fit their dataset. You must do this for all three kernels, which will yield three intermediate results. I see. So one operation takes place from this kernel, then this kernel, then this kernel. Alright. Then an element-wise sum is performed containing all three intermediate results, which I just discussed a bit before, along with the bias the network has learned. After this, the resulting two-dimensional tensor will be the activation map viewable on the interface above for the topmost neuron in the first convolutional layer. The same operation must be applied to produce each neuron's activation map. With a single map, we are able to reduce that there are 3 to 10, 30 unique kernels. Yep, one kernel for each of the each neuron this layer. Each of size 3 into 3 applied in the first convolutional layer. The connectivity between the convolutional layer and the previous layer is a design decision when building a new network architecture. Let's understand the hyperparameters here. Input size, okay, it's very simple. What about kernel size? I see this made up of four individual pixels. But stride, I believe would we need to increase the input size, increase by padding. This applies padding like artificial cells makes up data. Small kernel sizes are able to extract a much larger amount of information containing highly local features from the input. A smaller kernel size also leads to a smaller reduction in layer dimensions. Conversely, a large kernel size extracts less information, which leads to a faster reduction, meaning the process is done faster but leads to worse performance. Large kernels are better suited to extract features that are larger. So it kind of depends from image to image, is what they're saying. Stride indicates how many pixels on the kernel should be shifted over at a time. I see how many. If I set this to 2, it stops working. Okay, maybe I need to. Yeah, there you go. It switches over by each 2 pixels. Those 3 are covered. Padding is just you add. Yeah, often is when the kernel extends beyond the activation map. Yep. It's to preserve the tensors, original like dimensions and stuff. Is what I understand from that. Anyhow, Relu. Neural networks are extremely. My mic is yeah open, right? Neural networks are extremely prevalent with modern technology because they are so accurate. Yep, Relu. Uh, from memory again, Relu just takes in the yeah. If it's negative, it turns it into a zero. Else, it's a positive number anyway. It just outputs that. A softmax operation serves a key purpose, making sure that the CNN output sum to 1. Yep. Because of this, softmax operations are useful to scale model outputs into probabilities. Click on the last layer reveals the softmax operation in the network. Notice how the logics of the pattern are scaled between 0 to 1. For a visual indication of the impact of each logic, they are encoded using a light orange to dark orange color scale. After passing through the softmax function, each class now corresponds to an appropriate probability. All right. Okay. Okay. Gosh, I need to. Yeah. Oh, this is resolution fast. That's good. I'm feeling a bit sleepy today for some reason. Anyhow, what's Amazon doing here? Safety researcher at OpenAI. Seems like a super smart guy. Anyhow, I'll just
Will stay persistent for a longer
back to our
time.
video, yeah?
But of course, overnight it's going to disconnect. So I click reconnect. And then if I want to get back to wherever we were, because we downloaded some data from,
Let's start with us making the
torchvision.datasets, I have, but we're getting so close to training our model. Let's write some code to train our first CNN model. Training and testing. Just going to make another heading here. Model 2.
did we train this one? I think.
Using our training kernel can operate on what's going on here in the corner, in case there's some information on the edges of our image. Now you might be thinking, there's a whole bunch of values here. How do we know what to set them? Well, you notice that I've just copied exactly what is going on here.
Yeah, let's just do from the channels. I know we covered this, but just to get back into the zone again, we're gonna cover it once more.
Edges of our image. Now you might be thinking, Daniel, there's a whole bunch of, let's so that our kernel, if I jump, we have now evolving the matter. And finally, because a lot, then we're going to the style launch community plus for mode, out, comes the input. And then we have one. If we had color images, we would set the input image technology we've been using the whole time. Defining all of the components is do this when nn to get to the representation values here on the left. Block shape, put shape, that net, whole bunch of different resources. And also, how could you find out more about a convolutional neural network? What is a convolutional neural network? You can go through that. But let's
Run all.
stop that for a moment. Let's code this one up together. So we're going to initialize our class here, def init. We're going to pass it in an input shape, just like we often do. We're going to put in a number of hidden units, which is an int. And we're going to put in an output shape, which is an int. Wonderful. So nothing too outlandish that we haven't seen before there. And we're going to go super.init to initialize our initializer, for lack of a better way of putting it. Now, we're going to create our neural network in a couple of blocks this time. And you might often hear when you learn more about convolutional neural networks, or I'll just tell you that things are often referred to as convolutional blocks. So if we go back to our keynote, this combination of layers might be referred to as a convolutional block. And a convolutional block, a deeper CNN, might be comprised of multiple convolutional blocks. So to add to the confusion, a block is comprised of multiple layers, and then an overall architecture is comprised of multiple blocks. And so the deeper and deeper your models get, the more blocks it might be comprised of, and the more layers those blocks may be comprised of within them. So it's kind of like Lego, which is very fun. So let's put together an NN sequential. Now, the first few layers here that we're going to create in conv block 1 are nn.conv2d. Oh, look at that. Us writing our first CNN layer. And we have to define something here which is in channels. So this channels refers to the number of channels in your visual data. And we're going to put in input shape. So we're defining the input shape. This is going to be the first layer in our model. The input shape is going to be what we define when we instantiate this class. And then the out channels. Oh, what's the out channels going to be? Well, it's going to be hidden units, just like we've done with our previous models. Now, the difference here is that in nn.conv2d, we have a number of different hyperparameters that we can set. I'm going to set some pretty quickly here, but then we're going to step back through them, not only in this video, but in subsequent videos. Oh, we've got a fair bit going on here. We've got in channels.
This conv2d.
nn.conv2d. Oh, look at that. Us writing our first CNN layer. And we have to define something here which is in channels. So this channels refers to the number of channels in your visual data. And we're going to put in input shape. So we're defining the input shape. This is going to be the first layer in our model. The input shape is going to be what we define when we instantiate this class. And then the out channels. Oh, what's the out channels going to be? Well, it's going to be hidden units, just like we've done with our previous models. Now, the difference here is that in nn.conv2d, we have a number of different hyperparameters that we can set. I'm going to set some pretty quickly here, but then we're going to step back through them, not only in this video, but in subsequent videos. Oh, we've got a fair bit. going on here. We've got in channels, which is our input shape. We've got out channels, which are our hidden units. We've got a kernel size, which equals 3, or this could be a tuple as well, 3 by 3, but I just like to keep it as 3. We've got a stride and we've got padding. Now, because these are values we can set ourselves,
What up? Alright, that should be good enough.
what are they referred to as? Let's write this down. Values we can set ourselves in our neural networks, in
Hyperparameters,
our
right?
NNs, neural networks, are called hyperparameters. So these are the hyperparameters of NN-conv2D. And you might be thinking, what is 2D for? Well, because we're working with two-dimensional data, our images have height and width. There's also conv1D for one-dimensional data, 3D for three-dimensional data. We're going to stick with 2D for now. And so what do each of these hyperparameters do? Well, before we go through what each one of them do, we're going to do that when we step-by-step through this particular layer. What we've just done is we've replicated this particular layer of the CNN Explainer website. We've still got the relu, we've still got another conv and a relu and a max pool and a conv and a relu and a conv and a relu and a max pool. But this is the block I was talking about. This is one block here of this neural network, or at least that's how I've broken it down. And this is another block. You might notice that they're comprised of the same layers, just stacked on top of each other. And then we're going to have an output layer. And if you want to learn about where the hyperparameters came from, what we just coded, where could you learn about those? Well, one, you could go, of course, to the Pytorch documentation, Pytorch NN-conv2D. You can read about it there. There's a mathematical operation that we talked about or briefly stepped on before, or touched on, stepped on. Is that the right word? So create a conv layer. It's there. But also, this is why I showed you this beautiful website, so that you can read about these hyperparameters down here. Understanding hyperparameters. So your extra curriculum for this video is to go through this little graphic here and see if you can find out what padding means, what the kernel size means, and what the stride means. I'm not going to read through this for you. You can have a look at this interactive plot. We're going to keep coding, because that's what we're all about here. If in doubt, code it out. So we're going to now add a relu layer, and then after that, we're going to add another conv2D layer. And the in channels here is going to be the hidden units, because we're going to take the output size of this layer and use it as the input size to this layer. We're going to keep going here. Out channels equals hidden units again in this case. And then the kernel size is going to be 3 as well. Stride will be 1. Padding will be 1. Now, of course, we can change all of these values later on, but just bear with me while we set them how they are. We'll have another relu layer. And then we're going to finish off with the NN max pool 2D layer. Again, the 2D comes from the same reason.
Let's add the kernel size 3. So we're just copying all of this from the CNN Explain website, because they're replicating the tiny VGG model, which they have done too. So yeah, it's this.
Reason we use conv2D. We're working with 2D data here. And we're going to set the kernel size here to be equal to 2. And of course, this can be a tuple as well, so it can be 2, 2. Now, where could you find out about NN max pool 2D? Well, we go NN max pool 2D. What does this do? Applies a 2D max pooling over an input signal composed of several input planes. So it's taking the max of an input. And we've got some parameters here, kernel size, the size of the window to take the max over. Now, where have we seen a window before? I'm just going to close max of an input. And we've got some.
Let's see.
Well,
Let's listen to the
now, where did you find out about NN max pool 2D? Well, we go NN.
I mean, the kernel size for this one.
Max pool 2D. What does this do? Applies a 2D max pooling over an input signal composed of several input planes. So it's taking the max of an input. And we've got some parameters here, kernel size, the size of the window to take the max over.
Alright, so our two-dimensional tensor, it takes the max of everything.
Now, where have we seen a window before? I'm just going to close these. We come back up. Where do we see a window? Let's dive into the max pool layer. See where my mouse is? Do you see that 2 by 2? Well, that's a window. Now look at the difference between the input and the output. What's happening?
Is that 2 by 2 or 2 by 2?
See where my mouse is?
Oh, does it take 2 pixels? Is that okay? I think kind of understand what it means now. Just large this right now. It takes 2 pixels on the left side, and then is it 2 pixels or 4 pixels? But yeah, it's taking 4 pixels. Takes the max value out of all of them. Oh, the kernel size is 2, so it makes a 2 into 2 square. Is that what it means? And yeah, because it takes the max of each individual thing, it halves the number of pixels. I guess.
Do you see that 2 by 2? Well, that's a window. Now look at the difference between the input and the output. What's happening? Well, we have a tile that's 2 by 2,
There's
a window
a-
of 4, and the max, we're taking the max of that tile. In this case, it's 0. Let's find the actual value. There we go. So if you look at those 4 numbers in the middle, inside the max brackets, we have 0.07, 0.09, 0.06, 0.05, and the max of all those is 0.09. And you'll notice that the input and the output shapes are different. The output is half the size of the input. So that's what max pooling does, is it tries to take the max value of whatever its input is, and then outputs it on the right here. And so as our data, this is a trend in all of deep learning actually, as our image moves through, this is what you'll notice. Notice all the different shapes here. Even if you don't completely understand what's going on here, you'll notice that the 2 values here on the left start to get smaller and smaller as they go through the model. And what
Yeah, that's right. Or in other words, if I were to describe this in layman's term, the image becomes blurry as we move forward. It loses pixels.
our model is trying to do here is take the input and learn a compressed representation through each of these layers. So it's going to smush and smush and smush, trying to find the most generalizable patterns to get to the
can
ideal
use the
outputs.
word smush.
And that input is eventually going to be a feature vector to our final layer. So a lot going on there, but let's keep coding. What we've just completed is this first block. We've got a conv layer, a ReLU layer, a conv layer, a ReLU layer, and a max pool layer. Look at that. Conv layer, ReLU layer, conv layer, ReLU layer, max pool. Should we move on to the next block? We can do this one a bit faster now because we've already coded the first one. So
Conval, max pool. Relu, max pool. We're gonna replicate the same block again now.
I'm going to do nn.sequential as well.
Alright, let's switch back to coding mode now.
And then we're going to
Yep, just came up with it now. This is what we're gonna call it, coding mode. We can't copy the first one to be frank, but let's just type it out.
go nn.com2d. We're going to set the in channels. What should the in channels be here? Well, we're going to set it to hidden units as well because our network is going to flow just straight through all of these layers. And the output size of this is going to be hidden units. And so we want the in channels to match up with the previous layer's out channels. So then we're going to go out channels equals hidden units as well. We're going to set the kernel size. Kernel size equals 3, stride equals 1, padding equals 1. Then what comes next? Well, because the 2 blocks are identical, the conv block 1 and conv 2, we can just go the exact same combination of layers. nn ReLU, nn conv2d, in channels equals hidden units, out channels equals, you might already know this, hidden units. Then we have kernel size equals 3, 32, don't want it that big. Stride
For 3. I'm gonna apply a ReLU layer. We're gonna apply another convolutional layer. But this time the out channels, yeah, it would be because yeah, need 10 labels after all. What happened here? Let's switch positions.
equals 1, padding equals 1. What comes next?
ReLU layer. That came out a bit louder than expected. Hey, we have We have a chat going on here from what's it? Valsa123. Hey Valsa123. Welcome to my stream. How are you? How's your day? I'm doing good, thank you. Just learning some Python stuff here. Glad to hear you're doing good too. What happened to my chat section? It used to be here. Maybe it gets hidden. Due to machine learning? Um, would you consider? I don't know. I mean, I started learning this for the past. We're on day 9 now, so uh, new is subjective, I guess. I don't think I'm new to machine learning at this point. I know a bit, but yeah, I still have a lot to learn. What about you? Are you new to machine learning? I mean, are you a developer? What is that? Long lag. Okay, I think we have a bot there. Um, Alright, let's continue with video here.
Next. Well, we have another ReLU layer.
I've been trying to get a project going. Like I need to train an ML model, but it always overfits. What does the ML model do? Like, what's the project if you don't mind explaining? What's the project about? And to add a ReLU layer here.
ReLU, and then what comes after that?
A max pool.
We have another max pool. And then max pool 2D, kernel size equals 2. Beautiful. Now, what have we coded up so far? We've got this block, number 1. That's what this one on the inside here. And then we have com2, ReLU2, com2, ReLU2, max pool 2. So we've built these 2 blocks. Now, what do we need to do? Well, we need an output layer. And so, what did we do before when we made model 1? We flattened the inputs of the final layer before we put them to the last linear layer. So flatten. So this is going to be the same kind of setup as our classifier layer. Now, I say that on purpose because that's what you'll generally hear the last output layer.
It is supposed to detect drunk people from CCTV footage. Oh, alright. No, I'm pretty new to new as in, yeah, I still have a lot to learn on machine learning and stuff, but did you make the model using CNNs and stuff? It always overfits. Overfitting means that it looks into the training data more and it just doesn't work well with the testing data, right? Did you write it in? Of course, I would assume you wrote it in Python, but what module did you use? Like Pytorch or TensorFlow or what?
In a classification model called is a classifier layer. So we're going to have these 2 layers are going to be feature extractors. In other words, they're trying to learn the patterns that best represent our data. And this final layer is going to take those features and classify them into our target classes, whatever our model thinks best suits those features, or whatever our model thinks those features that it learned represents in terms of our classes. So let's code it out. We'll go down here. Let's build our classifier layer. This is our biggest neural network yet. You should be very proud. We have nn.sequential again. And we're going to pass in nn.flatten.
Bad on unseen data, perform well on trained data. Yeah. Well, I just guessed that's what overfitting means. I've heard it a couple of times in this space. Yeah, Python. where did you get the training and testing data for that? You found it like randomly on the internet, or like, where did you get it from?
because the output of the
Did you gather it yourself? What did you do to gather it? Went around to place with CCTV, or how do you do it? You know, one part of machine learning is the data gathering part, isn't it? Be right back. All right, sure.
these two blocks is going to be.
That's, yeah. Now we need to build a classifier.
And we're going to pass in nn.flatten because the output of the
I'm gonna flatten this and that thing because what the output
of these two
is?
blocks is going to be a multidimensional tensor, something similar to this size, 13, 13, 10. So we want to flatten the outputs into a single feature vector, and then we want to pass that feature vector to an nn.linear layer. And we're going to go in features equals hidden units times something times something. Now the reason I do to an nn.linear layer, and we're going to go in features equals hidden units times something times something. Now the reason I do this is because we're going to find something out later on, or times 0, just so it doesn't error. But sometimes calculating what your in features needs to be is quite tricky. And I'm going to show you a trick that I use later on to figure it out. And then we have out features.
Hmm. Why is it multiplying it with 0? Oh, I think it's just a placeholder for what he's about to explain, perhaps. Um, let's listen to it
Relates to our
first.
output shape, which will be the length of how many classes we have, right? One value for each class that we have. And so, with that being said, let's now that we've defined all of the components of our tiny VGG architecture, there's
Oh, now, man, let's just put along that.
a lot going on, but this is the same methodology we've been using the whole time, defining some components and then putting them together to compute in some way in a forward method. So forward self x. How are we going to do this? We're going to set x is equal to self conv block 1 x. So x is going to go through conv block 1. It's going to go through the conv2d layer, relu layer, conv2d layer, relu layer, max pull layer, which will be the equivalent of an image going through this layer, this layer, this layer, this layer, this layer, and then ending up here. So we'll set it to that, and then we can print out x.shape to get its shape. We'll check this later on. Then we pass x through conv block 2. Which is just going to go through all of the layers in this block, which is equivalent to the output of this layer going through all of these layers. And then because we've constructed a classifier layer, we're going to take the output of this block, which is going to be here, and we're going to pass it through our output layer, or what we've termed it, our classifier layer. I'll just print out x.shape
Oh, okay. So this is our output layer.
here, so we can track the shape as our model moves through the architecture. X equals self.classifier x. And then we're going to return x. Woohoo! Look at us go. We just built our first convolutional neural network by replicating what's on a CNN Explainer website. Now, that is actually very common practice in machine learning, is to find some sort of architecture that someone has found to work on some sort of problem and replicate.
Return X. I think that's a common practice across coding in general.
Look at us go. We just built our first convolutional neural network by replicating what's on a CNN Explainer website. Now, that is actually very common practice in machine learning, is to find some sort of architecture that someone has found to work on some sort of problem and replicate it with code and see if it works on your own problem. You'll see this quite often. And so now let's instantiate a model. We go torch.manual.c. We're going to instantiate our first convolutional neural network. Model 2 equals fashion mnist.
Let's run this.
We will go model v2, and we are going to set the input shape. Now, what will the input shape be? Well, I'll come 2D layer up here. The input shape is the number of channels in our images. So do we have an image ready to go? Image shape. This is the number of color channels in our image. We have 1. If we had color images, we would set the input shape to 3. So the difference between our convolutional neural network, our CNN, tiny VGG, and the CNN explainer, tiny VGG, is that they are using color images. So their input is 3 here. So 1 for each color channel, red, green, blue. Whereas we have black and white images, so we have only 1 color channel. So we set the input shape to 1. And then we're going to go hidden units.
Should we have? I guess not, because I was about to say, shouldn't we have 2 color channels, one for black and one for white? And I think that's a dumb question.
Equals 10, which is exactly the same as what tiny VGG has used. 10.
Although, let me just search it. No question is dumb. I take that back. Why do these images have only 1 color channel? Oh, okay. Grayscale images should not be confused with black and white images. Okay. So this is not black and white image. Oh, I see. Grayscale image only has 1 color channel because it's in between. No, grayscale image is in between 0 and 1, whereas the one with 2 color channels is just black and white. Yeah.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that sets the hidden units value of each of our layers. That's the power of creating an initializer with hidden units. And then finally, our output shape is going to be 1. We've seen this before. This is going to be the length of our class names. 1 value for each class in our data set. And of course, we're going to send this model to the device.
We have already got it.
Oh no, what did we get wrong? Out channels.
Did we also misspell it? I hope not.
Output shape? Where did I spell wrong? Out channels. I forgot an L.
User warning, initializing 0 element tensors is no.
Of course, typo. Oh, kernel size, another typo. Did you notice that? Kernel size.
That's right,
Where
Horse.
did we spell this wrong? Oh, here. Kernel size. Are there any other typos? Probably.
Oh, what's that? Are you a software engineer? Yes. I am a software engineer. I quit my 9 to 5 to basically get into machine learning and stream what I learned for the time being, at least. While my plan is to learn all that there is in AI and then jump to the ML field. What about you? You are a software engineer yourself?
Probably. Oh, beautiful. There we go. Okay, what have we got? Initializing 0 op tensors and non-op. Oh, so we
What were you doing before as a software engineer? Mainly I work with automations and stuff. I also dabbled a bit in making backend stuff, backend website stuff. But mainly I was working on making automation scripts in Python. I'm currently a final year student for software. That's good.
we've got an issue here. And
So
Eric
you're
picks up
planning to get into the job market, huh?
this, but this is just to, there's a trick to calculating this.
This is
We're going to cover this in another video.
Okay, tell
but
me what's
pat yourself on the back. We've written a fair bit of code here. This is a convolutional neural network that replicates the tiny VGG architecture on the CNN Explainer website. Now, don't forget, you're actually
You'll get there for sure.
curriculum is to go through this website for at least 20 minutes.
I would recommend you to, freelance a bit and then take that experience to get in a better job, maybe, something like that, perhaps. Most of the time, if the freelance work you do kind of turns out to be a full-time job later on. Do you get work from freelancing? Yeah, I do. I started off as a freelancer, and one of my freelancing gigs turned out into my previous software engineering job. And there are too many people competing for it. There are many people competing for it, but I mean, uh, you have to kind of figure it out. Like, how do I put this? See, there are many people competing out there in the freelance industry, yes, but if you can, if you are good, people will hire you. Is all I have to say. Um, yeah, there is, but look at it this way. When you freelance, you're directly talking to the person who wants, like, you're directly talking to the client rather than in a usual job where you talk to HR and stuff. What that means is they don't care what degree or anything that you have with you. They only care about what you can do to solve their problem, right? So if you can prove to the person on the other side that, hey, I am well suited for the job by showing them projects and stuff, they would message you, and hopefully that would turn out to be a job. So basically just get good. I mean, I guess, yeah, that's what I mean. Get good, yeah, but at the same time you also need to know how to kind of communicate. And then, because see, when you become a freelancer, your communication skills need to be top notch. Whereas in the other type of job, like a company based job, yeah, like you won't be the one who will communicate with clients and stuff. I hope that answers your question.
And read about what's happening in our models. We're focused on code here, but this is particularly where you want to pay attention to. If you read through this, understanding
Are you specializing in AI or something like that, or what do you wanna look for? Like, are you trying to get into full stack development or ML, or yeah? If you don't mind sharing, that is.
hyperparameters and play around with this, the next couple of videos will make a lot more sense. So read about padding, read about kernel size, and read about stride.
Yep,
I'll
we
see you in the next
already
video.
did that.
We're going to go through our network step by step. Welcome back. Now, I'm super stoked because in the last video, we coded together our first ever convolutional neural network in Pytorch. So, well done. We replicated the tiny VGG architecture from the CNN Explainer website, my favorite place for learning about CNNs in the browser. So now,
It says we have a new. I'm in my final year. Let me tell you, I have a. I mean, the important thing is for you to get started. I guess your first job, it doesn't matter what you do, I guess, because you'll be learning quite a lot in the job, is all I have to say. I swear. Yeah. I mean, it's true. It's true. Like, you learn quite a lot in your first job. Like, you sign up for something else, but what you do on the job would be something else entirely.
we introduced two new layers that we haven't seen before, Conv2D and Maxpool2D. But they all have the same sort of premise of what we've been doing so far, is that they're trying to learn the best features to represent our data in some way, shape, or form. Now, in the case of Maxpool2D, it doesn't actually have any learnable parameters. It just takes the max, but we're going to step through that later on. Let's use this video to step through NNConv2D. We're going to do that with code. So I'll make a new heading here, 7.1, stepping through NNConv2D. Beautiful. Now, where could we find out what's going on in NNConv2D? Well, of course, we have the documentation, NNConv2D. We've got Pytorch. So if you want to learn the mathematical operation that's happening,
Just look at the documentation for a bit. Applies a 2D convolution layer or an input channel. It takes the bias and does some crazy math over here. Right.
we have this value here, this
Oh, I'm from India.
operation here. Essentially, it's saying the output is equal to the bias term times something plus the sum of the weight times something times the input. So do you see how just the weight matrix, the weight tensor, and the bias value manipulating our input in some way equals the output? Now, if we map this, we've got batch size, channels in, height, width, channels out, out,
If you don't mind sharing, where are you from?
out, etc., etc. But we're not going to focus too much on this.
Is it hot ever there? I mean, it is, but I mean the state where I'm from Kerala. It's a state in India. It's pretty tropical over here, so the heat doesn't get too much. It's like it doesn't go over the extremes. It is neither too hot or too cold. It's somewhere in the middle. You're from Mauritius. I know I'm pronouncing that wrong. Probably I am. I am pronouncing that wrong. How do you pronounce that? Mauritius? Pronunciation.
Mauritius,
Mauritius. And what about this?
Mauritius,
Mauritius. What about this?
Mauritius,
Mauritius. I stick to this.
Mauritius,
Mauritius. I heard oh, thank you. Oh, you're it's on obvious that I'm seeing that your Twitch ID is base, not what was I calling you? Waltz or something, right? Thank you for the follow. I appreciate it. Very beautiful, beautiful place that you have there.
If you'd like to read more into
Must
this, you
be
can. Let's
kind of tropical climate for you too there, I guess. Or maybe it's too hot over there because you asked me whether it's hot here.
try it with code. And we're going to reproduce this particular layer here, the first layer of the CNN Explainer website, and we're going to do it with a dummy input. In fact, that's one of my favorite ways to test.
Oh, currently it's hot. Oh, it is cold. Okay. I mean, if if I were to just judge by looking at the image, I would imagine that it would be tropical over here. Huh. Coldest it has ever been. Well, yeah, it doesn't really get very, very cold over here in India. Like, it doesn't snow. It snows over there in the northern side of India, but never here. Does it snow over there, or is it like just like really cold? Normally it is hot. Yeah, I mean that figures. Yeah,
Test things. So I'm just going to link here the documentation,
that
See the
doesn't
documentation
snow over there,
for-
does it?
and then column 2D here. And if you'd like to read through more of this, of course, this is a beautiful place to learn about what's going on. There's the shape, how to calculate the shape, height out, width out, etc. That's very helpful if you need to calculate input.
Or is this go back?
In fact, that's one of my favorite ways to test things. So I'm just going to link here the documentation, see the documentation for, and then column 2D here. And if you'd like to read through more of this, of course, this is a beautiful place to learn about what's going on. There's the shape, how to calculate the shape, height out, width out, etc. That's very helpful if you need to calculate input and output shapes. But I'll show you my trick for doing so later on.
All right.
We have here, let's create some dummy
Show
data.
me your
So
trick.
I'm going to set
That's fine. I mean, it's my fault. I need to set some kind of like a schedule. Like, you know how some streamers have a Pomodoro timer? I need to set something like that, maybe. It's fine though. Thank you. Thank you for your concern.
that Torch manual seed. We need it to be the same size as our CNN explainer.
I just wanna get over to my like, target that I usually set in my mind for the day.
64, 64, 3, but we're going to do it Pytorch style. This is color channels last. We're going to do color channels
Would
first.
you look at that?
So,
Our
yeah,
viewer count
that's
is
all.
also
We're
increasing.
going to be writing torch.randn, and we're going to pass in size equals 32, 3, 64, 64. And then we're going to create a singular image by taking the first of that, so image is 0. Now let's get the image batch shape, because a lot of machine learning, as I've said before, and
They're just creating random numbers. So yeah,
deep learning that, so image pass in size equals 32, 3, 64, 64. And then we're going to create a singular image by taking the first of that, so image is 0. Now let's get the image batch shape, because a lot of machine learning, as I've said before, and deep learning is making sure your data has the right shape. So let's check images.shape, and let's check single image shape. We're going to go test image.shape, and finally, we're going to print, what does the test image look like? We'll get this on a new line, hey? New line, test image. This is, of course, not going to be an actual image. It's just going to be a collection of random numbers. And, of course, that is what our
match shape and oh, we have another message. Did you go to uni? I leave that for you to guess. Type yes or no from just guess first and I'll answer that. What do you think? Did I go to uni or not? Ah, you guessed correct. Nah, I did not go to university. I'll take that as a compliment. I am young, by the way. I'm not old. Let's see what this simply means shape is. I'm just printing the test image.
Our model is currently comprised of model 2. If we have a look at what's on the insides, we are going to see a whole bunch of
See, so three color channels, 64 pixels high and 64 pixels wide.
random numbers. Look at all this.
It depends. I mean, I'm not totally against uni or anything. Some people, for some people, it's actually better to go to university, but it depends. Yeah, I mean, if you were to ask me, I would always recommend getting experience and things first. Like it's as I mentioned, no one cares. No, like I don't think anyone other than HR people care what degree you have. That at the end of the day, they only care if you can do the job or not.
What do we have? We scroll up. It's going to give us a name for something. We have conv block 22. Look at all this. That is what our model is currently comprised of. Model 2, if we have a look at what's on the insides, we are going to see a whole bunch of random numbers. Look at all this. What do we have? We scroll up. It's going to give us a name for something. We have conv block 22. We have a weight. We have a bias. Keep going up. If we go right to the top, we have another weight. Keep going down, we have a bias, a weight, etc., etc. Now, our model is comprised of random numbers, and what we are trying to do is just like all of our other models, is pass data in and adjust the random numbers within these layers to best represent our data. So let's see what happens if we pass some random data through one of our conv2D layers. So let's go here. We're going to create a single conv2D layer. So conv layer equals, what does it equal? And then conv2D, we're going to set the in channels is equal to what? Oh, reveal the answer too quickly. 3. Why is it 3? Well, it's because the in channels is the same number of color channels as our images. So if we have a look at our test image,
grayscale images, it would be 1.
Shape. What do we have? 3. It has 3 color channels. That is the same as the value here, except the order is reversed. This is color channels last. Pytorch defaults to color channels first. So
what is color channel last? Sorry.
Color channels as our images. So if we have a look at our test image, shape, what do we have? 3. It has 3 color channels. That is the same as the value here.
Alright, see ya. Wiser. Thank you for the follow, by the way. Take care. Bye.
Except the order is reversed. This is color channels last. Pytorch defaults to color channels first. So, or for now it does. In the future this may change, so just keep that in mind. So out channels equals 10. This is equivalent to the number of hidden units we have. 1, oh, I don't want that one just yet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have that 10 there. So we have 10 there. Then we have kernel size. Oh, what is the kernel? Well, it's not KFC, I can tell you.
Okay, see. Okay. So yeah, 3. Then
That. And then we have stride, and then we have padding. We're gonna step through
why did I make this setup? Though?
these in a second. But let's check out the kernel.
So I guess it would make it as 3 into 3, but we can define what the kernel size should be.
And this kernel can also be 3 by 3, but it's a shortcut to just type in 3. So that's what it actually means if you just type in a single number. It's equivalent to typing in a tuple. Now, of course, you could find that out by reading through the documentation here. But where did I get that value? Well, let's dive into this beautiful website, and let's see what's happening. So we have a kernel here, which is also called a filter. So the thing I'm talking about is this little square here, this kernel. Oh, we can see the weights there up the top. This is how beautiful this website is. So if we go over there, this is what's going to happen. This is a convolution. It starts with this little square, and it moves pixel by pixel across our image, and you'll notice that the output is creating some sort of number there, and you'll notice in the middle we have a mathematical operation. This operation here is what's happening here. Right, weight times the input. That's what we've got there. Now the beauty of Pytorch is it does all of this behind the scenes for us. So again, if you'd like to dig more into the mathematical operation behind the scenes, you've got the resource here, and you've also got plenty of other resources online. We're going to focus on code for now. So if we keep doing this across our entire image, we get this output over here. So that's the kernel. And now where did I get 3 by 3 from? Well, look at this. 1, 2, 3, 1, 2, 3, 1, 2, 3. 3 by 3, we have 9 squares. Now if we scroll down, this was your extracurricular. 1, 2, 3, 1, 2, 3.
Oh, Okay, that makes a hell lot of sense now. If the kernel size was 4 into 4, we would have 16 computations going on.
3, 1, 2, 3. 3 by 3, we have 9 squares. Now, if we scroll
This
down,
is
this was your
best.
extra curriculum for the last video. Understanding hyperparameters. What happens if we change the kernel size to 3 by 3? Have a look at the red square on the left. Now, if we change it to 2 by 2, it changed again. 3 by 3, this is our kernel, also known as a filter, passing across our image, performing some sort of mathematical operation. And now the whole idea of a convolutional layer is to try and make sure that this kernel performs the right operation to get the right output over here. Now, what do these kernels learn? Well, that is entirely up to the model. That's the beauty of deep learning, is that it learns how to best represent our data, hopefully, on its own, by looking at more data. And then so if we jump back in here, so that's the equivalent of setting kernel size 3 by 3. What if we set the stride equal to 1? Have we got this in the right order? It doesn't really matter. Let's go through stride next. If we go to here, what does stride say? Stride of the convolution, of the convolving kernel. The default is 1. Wonderful. Now, if we set the stride, or if we keep it at 1, it's a default 1, it's going to hop over. Watch the red square on the left. It's going to hop over 1 pixel at a time. So the convolution, the convolving, happens 1 pixel at a time. That's what the stride sets. Now, watch what happens when I change the stride value to the output shape. Wow. Do you notice that it went down? So we have here, the kernel size is still the same, but now we're jumping over 2 pixels at a time. Notice how on the left, 2 pixels become available, and then if I jump over again, 2 pixels. So the reason why the output compresses is because we're skipping some pixels as we go across the image. And now this pattern happens throughout the entire network. That's one of the reasons why you see the size of our input, or the size of each layer, go down over time. What our convolutional layer is doing, and in fact, a lot of deep learning neural networks do, is they try to compress the input into some representation that best suits the data. Because it would be no point of just memorizing the exact patterns. You want to compress it in some way. Otherwise, you just might as well move your input data around. You want to learn generalizable patterns that you can move. It would be no point, neural networks do, is they try to compress the input into some representation that best suits the data. Because it would be no point of just memorizing the exact patterns. You want to compress it in some way. Otherwise, you just might as well move your input data around. You want to learn generalizable patterns that you can move around. And so we keep going. We've got padding equals 0. Let's see what happens here. If we change the padding value, what happens? Up, down. Notice the size here. Oh, we've added 2 extra pixels around the edge. Now if we go down, 1 extra pixel. Now if we go 0. Now why might we do that? If we add some padding on the end, well, that's so that our kernel can operate on what's going on here in the corner, in case there's some information on the edges of our image. Now you might be thinking, Daniel, there's a whole bunch of values here. How do we know what to set them? Well, you notice that I've just copied exactly what is going on here. There's a 3 by 3 kernel, there's no padding on the image, and the stride is just going 1 by 1. And so that's often very common in machine learning, is that when you're just getting started and you're not sure what values to set these values to, you just copy some existing values from somewhere and see if it works on your own problem. And then if it doesn't, well, you can adjust them. So let's see what happens when we do that. So pass the data through the convolutional layer. So let's see what happens. Conv output equals conv layer. Let's pass it our test image. And we'll check the conv output. What happens? Oh. Equals conv layer. Let's pass it our test image. And we'll check the conv output. What happens? Oh no, we get an error. Of course we get a shape error. One of the most common issues of machine learning and deep learning.
But I didn't get the shape error. Something might be wrong here. 3, 10, 3, 1, 0.
So this is saying that our input for the conv layer expects a 4-dimensional tensor, except it got a 3-dimensional input size of 364. Now, how do we add an extra dimension to our test image?
But then I didn't get that error, did I? I mean, this has 4 dimensions. Why didn't I get that error?
Let's have a look. How would we add a batch dimension over on the left here? We can go unsqueeze 0. So now we have a 4-dimensional tensor. Now,
Cool, but I did not get the error. What's going on here?
notice how on the left 2 pixels become available, and then if I jump over again, 2 pixels. So the reason why the output compresses is because we're skipping some pixels as we go across the image. 2 pixels by looking at ID changed again. Type in a single number. But let's check out the kernel. And this
Then it can't be, but let's just go with
kernel can also be 3 by 3, but it's a shortcut to just type in 3. So that's what it actually means if you just
that's just
type into this beautiful number and adjust this. We're image is just going to what is it? And deep learning is we're going to go test image dot shape, and finally we're going to print what is the test of random numbers. And of course that is what our model is currently. Scroll up is going to default to color channels first. So 3 color channels as our images. So if we have a look at our test image shape, well, if we com 2D, last data keep going down. Actual image is just going to be what does the test image look like? Shape, make the
what
images
does
0.
our model
Well,
do?
of course we have the document com 2D. Beautiful. Now, so if you want to learn, the first of that is making sure to create and read. What do we have? 3. It has 3 color channels. That is the same as the value here, except the order is reversed. This is color channels last. Pytorch defaults to color channels first. So, or for now it does. In the future this may change, so just keep that in mind. So out channels equals 10. This is equivalent to the number of hidden units we have. So we have 10 there. Then we have kernel. And this kernel can also be 3 by 5 reading called a filter. So if we go across our is so to our model. And so if we jump through time. To the output, now we're jumping, we're skipping. You see a lot of deep learning. No point. here. We add some, you might be thinking, well, just getting started and you're not sure what values to set these values to. You just copy some existing values from somewhere and see if it works on your own problem. And then if it doesn't, well, you can adjust them. So let's see what happens when we do that. So pass the data. Let's pass it our test image. One of the most common issues of learning. Now we're on the left. This,
I didn't get
what am I on? I think this could
that
be Colab, but
document.
if it's just all different to what's, if your numbers are different to what's on my screen, don't worry too much. Why is that? Because our conv layer is instantiated with random numbers, and our test image is just random numbers as well. What we're paying attention to is the input and output shapes. Do you see what just happened? We put our input image in there with 3 channels, and now because we've set out channels to be 10, we've got 10, and we've got 62, 62, and this is just the batch size, it just means one image. So essentially our random numbers, our test image, have gone through the convolutional layer that we created, have gone through this mathematical operation with regards to all the values that we've set. We put the weight tensor, well actually Pytorch created that for us. Pytorch has done this whole operation for us. Thank you, Pytorch. It's gone through all of these steps across. You could code this all by hand if you want, but it's a lot easier and simpler to use a Pytorch layer. And it's done this, and now it's created this output. Now, whatever this output is, I don't know. It is random numbers, but this same process will happen if we use actual data as well. So let's see what happens if we change the values. Kernel size, we increase. Notice how our output has gotten smaller because we're using a bigger
Alright, okay. Yep, makes sense.
kernel to convolve across the image. What if we put this to 3.3 back to what it was and stride of 2? What do you think will happen? Well, our output size basically halves because we're skipping 2 pixels at a time. Put that back to 1. What do you think will happen if we set padding to 1? 64, 64. We get basically the same size because we've added an extra pixel around the edges. Padding to 1. 64, 64. We get basically the same size because we've added an extra pixel around the edges. So you can play around with this, and in fact, I encourage you to do this is what we just did. Padding 1, we just added an extra dummy 0 pixel around the edges. So practice with this, see what happens as you pass our test image, random numbers, through a conv2D layer with different values here. What do you think will happen if you change this to 64? Give that a shot, and I'll see you in the next video. Who's ready to step through the NN Max Pool 2D layer? Put your hand up. I've got my hand up, so let's do it together, hey? We've got 7.2. Now, you might have already given this a shot yourself. Stepping through NN Max Pool 2D. And this is what I do for a lot of different concepts that I haven't gone through before, is I just write some test code and see what the inputs and outputs are. And so where could we find out about Maxpool 2D? Well, of course, we've got the documentation. I'm just going to link this in here. Maxpool 2D. In the simplest case, the output value of layer with input size NCHW, output, NCHout, WOut. By the way, this is number of batches, color channels, height, width, and this is the output of that layer. And kernel size, which is a parameter up here, KHKW, can be precisely described as out is going to be the max of some value, depending on the kernel size and the stride. So let's have a look at that in practice. And of course, you can read further through the documentation here. I'll just grab the link for this, actually. So it's here. Wonderful. And let's now first try it with our test image that we created above. So just highlight what the test image is. A bunch of random numbers in the same shape as what a single image would be if we were to replicate the image size of the CNN explainer. By the way, we'll have a look at a visual in a second of Maxpool here, but you can go through that on your own time. Let's, if in doubt, code it out. So we're going to print out the original image shape without unsqueezed dimension. Because recall that we had to add an extra dimension to pass it through our conv2D layer. Now, if you're using a later version of Pytorch, you might not get an error if you want to use a 3-dimensional image tensor and pass it through a conv layer. So we're going to pass it in test image original shape, test image.shape. So this is just going to tell us what the line of code in the cell above tells us, but that's fine. I like to make pretty printouts, you know? Test image with unsqueezed dimension.
Let's do this.
So this is just going to be our test image, and we're going to see what happens when we unsqueeze a dimension. Unsqueeze on the 0th dimension, that is. I was about to say first, but it's the 0th. Now we're going to create a sample NN Maxpool 2D layer, because remember, even layers themselves in torch.nn are models of their own accord, so we can just create a single, this is like creating a single layer model here. We'll set the kernel size equal to 2, and recall, if we go back to CNN Explainer, of their own accord, so we can just create a single, this is like creating a single layer model here. We'll set the kernel size equal to 2, and recall, if we go back to CNN Explainer, kernel size equal to 2 results in a 2x2 square, a 2x2 kernel that's going to convolve over our image, like so. And this is an example input and example output. And you can see the operation that max pooling does here. So just keep that in mind as we pass some sample data through our max pool layer. And now let's pass data through it. Well, actually, we'll pass it through just the conv layer first. Through just the conv layer. Because that's sort of how you might stack things. You might put a convolutional layer and then a max pool layer on top of that convolutional layer. So test image through conv. We'll create a variable here, equals our conv layer. Is going to take as an input our test image.unsqueeze on the 0th dimension again. Beautiful. Now we're going to print out the shape here.
Let's actually just look at that print statement first.
this is just highlighting how I like to troubleshoot things, is I do one step, print the shape, one step, print the shape, see what is happening.
as we go through.
As our data moves through various layers. So test image through conv.shape. We'll see what our conv layer does to the shape of our data.
Right, let's see for ourselves.
And then we're going to pass data through the max pool layer, which is a layer we created a couple of lines above, this one here. So let's see what happens. Test image through, can't type at the moment, through conv and max pool. So quite a long variable name here, but this is to help us avoid confusion of what's going on. So we go test image through conv. So you notice how we're taking the output of our convolutional layer, this here,
And we're passing,
it through our max pool layer, which has another typo. Wonderful. And finally, we'll print out the shape after going through.
Well, basically we're just stepping through each layer right now and seeing what the output is. Manually, I would say. Anyhow, test image through. Oh, yeah, there we go. Why do I keep on misspelling this? Okay, there we go.
Through conv layer and max pool layer. What happens here? So we want test image through.
And we'll copy this first, and then we'll, because I don't want to type out that long of a sentence.
Conv and max pool. Let's see how our max pool layer manipulates our test image's shape. You ready? 3, 2, 1, let's go. What do we get? Okay, so we have the test image.
Let's look at it through first ourselves, and then we'll follow the video. So, test image original shape. Alright, okay. Test image unsqueeze dimension. I don't think I need to unsqueeze it though, because for some reason the Pytorch in this version seems to do things under the hood. Maybe I might be wrong. Anyhow, after going through conv layer, it splits each three images, like each three like sub image into 10 image of its own. And max pool, since the kernel size is 2, it halves the 64 to 64 image into 32 into 32 image. Let's not unsqueeze our let's not unsqueeze and see if this works. It does. I guess Python fixed itself.
Original shape. Recall that our test image is just a collection of random numbers. And of course, our conv layer is going to be instantiated with random numbers. And max pool actually has no parameters. It just takes the maximum of a certain range in a tensor. So when we unsqueeze the test image as the input, we get an extra dimension here. When we pass it through our conv layer, oh, where did the 64 come from? 1, 64, 64, 64. Let's go back up to our conv layer. Do you notice how that we get the 64 there because we changed the out channels value? If we change this back to
We didn't change the out channels.
10, like what's in the CNN explainer model, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What do you think will happen there? Well, we get a little highlight here, 10. Then we keep going. I'll just get rid of this extra cell. We don't need to check the version anymore. We'll check the test image shape, still 364, 64. But then as we pass it through the conv layer here, we get a different size now. So it originally had 3 channels as the input for color channels, but we've upscaled it to 10 so that we have 10 hidden units in our layer. And then we have 64, 64. Now, again, these shapes will change if we change the values of what's going on here. So we might put padding to 0. What happens there? Instead of 64, 64, we get 62, 62. And then what happens after we pass it through the conv layer and then through the max pool layer? We've got 1, 10, 64, 64, and now we have 1, 10, 32, 32. Now, why is that? Well, let's go back into the CNN Explainer, jump into this max pool layer here. Maybe this one because it's got a bit more going on. Do you notice on the left here is the input? And we've got a 2x2 kernel here. And so the max pooling layer, what it does is it takes the maximum of whatever the input is. So you notice the input is 60, 60 in this case, whereas the output over here is 30, 30. Now, why is that? Well, because
Even though it takes 4 squares, it doesn't shift like to the next. So that's why it's half rather than 1/4. If that's the word. Anyhow, where's the max pool layer? Yeah. Oh no. Then should it be? Okay, maybe if it goes down. Can't tell if it go- yeah, it doesn't move down. It repeats the pixels. That's why
the max operation here is reducing it from section of 4 numbers. So let's get one with a few different numbers. There we go, that'll do. So it's taking it from 4 numbers and finding the maximum value within those 4 numbers here. Now, why would it do that? So, as we've discussed before, what deep learning neural network is trying to do, or in this case a CNN, is take some input data and figure out what features best represent whatever the input data is and compress them into a feature vector that is going to be our output. Now, the reason being for that is because you could consider it from a neural network's perspective is that intelligence is compression. So you're trying to compress the patterns that make up actual data into a smaller vector space, go from a higher dimensional space to a smaller vector space in terms of dimensionality of a tensor. But still, this smaller dimensionality space represents the original data and can be used to predict on future data. So that's the idea behind max pool is, hey, if we've got these learned features from our convolutional layers, will the most important patterns stay around if we just take the maximum of a certain section? So do you notice how the input here, you can still see the outline of the car here, albeit a little bit more pixelated, but just by taking the max of a certain region, we've got potentially the most important feature of that little section.
Because the most important feature is supposed to be more like there would be more data flowing in there, right? I guess that's the ideology or concept behind it.
And now, of course, you could customize this value here. If when we create our max pool layer, you could increase the kernel size to 4x4. Well, what do you think will happen if we increase it to 4? So here we've got a 2x2 kernel. If we increase it to 4x4, what happens?
16.
Do you notice that we've gone from 62 to 15? We've essentially divided our feature space by 4. We've compressed it even further. Now, will that work? Well, I'm not sure. That's part of the experimental nature of machine learning, but we're going to keep it at 2 for now. And so this is with our tensor here, 64, 64. But now let's do the same as what we've done above, but we'll do it with a smaller tensor so that we can really visualize things. And we're going to just replicate the same operation that's going on here. So let's go here. We'll create another random tensor. We'll set up the manual seed first. And we're going to create a random tensor with a similar number of dimensions. Now recall dimensions don't tell you, so this is a dimension. 1, 3, 64, 64. That is a dimension. The dimensions can have different values within themselves. So we want to create a 4-dimensional tensor to our images. So what that means is, let me just show you, it's way easy to explain things when we've got code, is torch.randn, and we're going to set it up as size equals 1, 1, 2, 2. We're going to have a look at this random tensor. It's got 4 dimensions. 1, 2, 3, 4. So you can have 1, 2, 2. We're going to have a look at this random tensor. It's got 4 dimensions. 1, 2, 3, 4. So you can have a batch size, color channels, and height width. A very small image, but it's a random image here. But this is quite similar to what we've got going on here, right? 4 numbers. Now, what do you think will happen if we create a max pool layer, just like we've done above? Create a max pool layer. So we'll go max pool. Layer. Just repeating the code that we have in the cell above. That's all right. A little bit of practice. Kernel size equals 2. And then we're going to pass the random tensor through the max pool layer. So we're going to max pool tensor equals max pool layer, and we're going to pass it in the random tensor. Wonderful. And then we can print out some shapes and print out some tensors, as we always do, to visualize, visualize, visualize. So I'm going to write in here max pool tensor on a new line. We'll get in the max pool tensor. We'll see what this looks like, and we'll also print out max pool tensor shape. And we can probably print out random tensor itself as well as its shape as well. We'll get the shape here, dot shape, and we'll do the same for the random tensor. So print. We get a new line, random tensor, new line, random tensor, and then we get the shape.
Right, let's see how fast we can type now. this and then do this. Because we don't shape. This is just to dot size, just to refresh our memory. Then, yeah, then the random tensor and its shape.
Random tensor shape, random tensor. Oh, a lot of coding here, but that's the fun part about machine learning, right? You get to write lots of code. Okay. So we're visualizing what's going on with our random tensor. This is what's happening within the max pool layer. We've seen this from a few different angles now. So we have a random tensor.
Where is this random tensor? Why do we have random tensor again here? Let's remove that. This is a random tensor. 1, 1, 2, 2, right? We have shape here. We take the max pool. Current size is 2. Reduces that to
Tensor
1,
numbers.
1.
We've got a size here. But the max pool tensor, once we pass our random tensor through the max pool layer, what happens? Well, we have 0.3367, 1288, 2345, 2303. Now, what's the max of all these? Well, it takes the max here is 3367. Oh, and we've got the random tensor down there. We don't want that. And see how we've reduced the shape from 2 by 2 to 1 by 1? Now, what's going on here? Just for one last time to reiterate.
It creates a square like this and then takes the max value, like removes these 3, like it just puts them out of the door for you.
The convolutional layer is trying to learn the most important features within an image. So if we jump into here, now what are they? Well, we don't decide what a convolutional layer learns. It learns these features on its own. So the convolutional layer learns those features. We pass them through a ReLU, nonlinear activation, in case our data requires nonlinear functions. And then we pass those learned features through a max pool layer to compress them even further. So the convolutional layer can compress the features into a smaller space, but the max pooling layer really compresses them. So that's the entire idea. One more time, we start with some input data, we design a neural network, in this case a convolutional neural network, a really compressed pool layer, to compress them even further through a ReLU, nonlinear activation, in case our data requires nonlinear functions. And then we pass those, the convolutional layer learns those features. We pass them through a ReLU, nonlinear activation, in case
Wait, let's listen to
within an image. So if we jump into here, now what are they? Well, we don't decide what a convolutional layer learns. It learns these features on its own. So the convolutional layer learns those features. We pass them through a ReLU, nonlinear activation, in case our data requires nonlinear functions. And then we pass those learned features through a max pool layer to compress them even further. So the convolutional layer can compress the features into a smaller space, but the max pooling layer really compresses them. So that's the entire idea. One more time, we start with some input data, we design a neural network, in this case a convolutional neural network, to learn a compressed representation of what our input data is, so that we can use this compressed representation to later on make predictions on images of our own. And in fact, you can try that out if you wanted to. Click here and add your own image. So I give that a go. That's your extension for this video. But now we step through the max pool 2D layer and the conv 2D layer. I think it's time we started to try and use our tiny VGG network. This is your challenge, is to create a dummy tensor and pass it through this model. Pass it through its forward layer and see what happens to the shape of your dummy tensor as it moves through conv block 1 and conv block 2. And I'll show you my trick to calculating the in features here for this final layer, which is equivalent to this final layer here. I'll see you in the next video. Over the last few videos, we've been replicating the tiny VGG architecture from the CNN Explainer website. And I hope you know that this is actually quite exciting because years ago, this would have taken months of work. And we've broken it down over the last few videos and rebuilt it ourselves with a few lines of Pytorch code. So that just goes to show how powerful Pytorch is and how far the deep learning field has come. But we're not finished yet. Let's just go over to our keynote. This is what we've done. CNN Explainer model. We have an input layer. We've created that. We have conv2D layers. We've created those. We have ReLU activation layers. We've created those. And finally, we have pooling layers. And then we finish off with an output layer. But now let's see what happens when we actually pass some data through this entire model. And as I said before, this is actually quite a common practice, is you replicate a model that you found somewhere and then test it out with your own data. So we're going to start off by using some dummy data to make sure that our model works. And then we're going to pass through, I've got another slide for this. By the way, here's a breakdown of Torch NM Conv 2D, if you'd like to see it in text form. Nothing here that we really haven't discussed before, but this will be in the slides if you would like to see it. Then we have a video animation. We've seen this before.
I'm gonna take a break for a few minutes and then I'll be right back. me switch back to my overlayer. Oops, wrong overlay. There we go. Where's my hair standing? Yep. All right. Yeah, let's continue with our Pytorch journey. I'm back from my break here. Oof, it is way sunnier than I expected. Anyhow,
Though. And plus, I'd rather you go through the CNN Explainer website on your own and explore these different values rather than me just keep talking about it. Here's what we're working towards doing. We have a fashion MNEST dataset, and we have our inputs. We're going to numerically encode them. We've done that already. Then we have our convolutional neural network, which is a combination of convolutional layers of our input and explore these different values rather than me just keep talking about it. Here's what we're working towards doing. We have a fashion MNEST dataset, and we have our inputs. We're going to numerically encode them. We've done that already. Then we have our convolutional neural network, which is a combination of convolutional layers, nonlinear activation layers, pooling layers. But again, these could be comprised in many different ways, shapes, and forms. In our case, we've just replicated the tiny VGG architecture. And then finally, we want to have an output layer to predict what class of clothing a particular input image is. And so let's go back. We have our CNN model here, and we've got model 2. So let's just practice a dummy forward pass here. We're going to come back up a bit to where we were. We'll make sure we've got model 2. And we get an error here.
Speed down model 2 again, but this time suited for grayscale images. Set our manual seed first of all. I mean, we can just go up and change it, can't we? Or even better, copy this model 2. Oh, it's already suited for grayscale images.
Because I've times this by 0. So I'm going to just remove that and keep it there. Let's see what happens if we create a dummy tensor and pass it through here. Now, if you recall where our image is, do we have image? This is a fashion MNIST image. So I wonder if we can go plot.im.imshow image, and I'm going to squeeze that, and I'm going to set the CMAP equal to gray.
Let's do that.
So this is our current image. Wonderful. So there's our current image. So let's create a tensor. Or maybe we just try and pass this through the model and see what happens. How about we try that? Model, image. Right, we're going to try the first pass, forward pass. So pass, image, through, model. What's going to happen? Well, we get an error. Another shape mismatch. We've seen this before. How do we deal with this? Because what is the shape of our current image?
Double object is not callable. When we passed in the image, what's happening here? And 49. That should be why. Rerun that and rerun this. Well, first we need to reinstantiate this and then rerun this. Alright, shape is match. Turn into 49 and 0 to 10.
1, 28, 28. Now, if you don't have this image instantiated, you might have to go back up a few steps. Image through model. What's going to happen? Well, we get an error. Another shape mismatch. We've seen this before. How do we deal with this? Because what is the shape of our current image? 1, 28. Now, if you don't have this image instantiated, you might have to go back up a few cells. Where did we create image? I'll just find this. So we created this a fairly long time ago, so I'm going to probably recreate it down the bottom. My goodness, we've written a lot of code. Well done to us. We could create a dummy tensor if we wanted to.
Good to us.
How about we do that? And then if you want to find, oh, right back up here, we have an image. How about we do that? We can just do it with a dummy tensor. That's fine. We can create one of the same size. But if you have image instantiated, you can try that out. So there's an image. Let's now create an image that is, or a random tensor that is the same shape as our image. So rand image tensor equals what? Torch.randn. And we're going to pass in size equals 1, 28, 28. Then if we get rand image tensor, we check its shape, what do we get? So the same shape as our test image here, but it's just going to be random numbers. But that's okay. We just want to highlight a point here of input and output shapes. to make sure our model works. Can our random image tensor go all the way through our model? That's what we want to find out. So we get an error here. We have 4 dimensions, but our image is 3 dimensions. How do we add an extra dimension for batch size? Now, you might not get this error if you're running a later version of Pytorch. Just keep that in mind. So unsqueeze 0. Oh, expected all tensors to be on the same device, but found at least 2 devices. Again. We're going through all the 3 major issues in deep learning. Shape mismatch.
That should have worked.
Device mismatch, data type mismatch. So let's put this on the device to target device, because we've set up device agnostic code. Mat1 and Mat2 shapes cannot be multiplied. Oh, but we get an output here. That is very exciting. So what I might do is move this a couple of cells up so that we can tell what's going on. I'm going to delete this cell. So where do these shapes come from? Well, we printed out the shapes there. And so this is what's happened when I'll just create our random tensor. I'll bring our random tensor up a bit too. Let's bring this up. There we go. So we pass our random image tensor through our model, and we've made sure it's got 4 dimensions by unsqueeze 0. And we make sure it's on the same device as our model because our model has been sent to the GPU. And this is what happens as we pass
It
our
passes it through the first convolutional block, turns it into a 14 by 14 image. Does the same to the second convolutional block, turns it into a 7 into 7 image.
Tensor, we've got 128, instead of previously we've seen 64, 64, 3. Just going to clean this up a bit. And we get different shapes here. So you'll notice that as our input, if it was 64, 64, 3 goes through these layers, it gets shaped into different values. Now, this is going to be universal across all of the different data sets you work on. You will be working with different shapes. So it's important to, and also quite fun, to troubleshoot what shapes you need to use for your different layers. So this is where my trick comes in. To find out the shapes for different layers, I often construct my models, how we've done here, as best I can with the information that I've got, such as replicating what's here. But I don't really know what the output shape is going to be before it goes into this final layer. And so I recreate the model as best I can, and then I pass data through it in the form of a dummy tensor in the same shape as my actual data, so we can customize this to be any shape that we wanted. And then I print the shapes of what's happening through each of the forward pass steps. And so if we pass it through this random tensor through the first conv block, it goes through these layers here, and then it outputs a tensor with this size. So we've got 10 because that's how many output channels we've set, and then 14, 14 because our 28, 28 tensor has gone through a max pool 2D layer and gone through convolutional layer, and then it goes through the next block, conv block 2, which is because we've put it in the forward method here, and then it outputs the shape, and if we go back down, we have now a shape of 1, 10, 7, 7. So our previous tensor, the output of conv block 1, has gone from 14, 14 to 7, 7. So it's been compressed. So let me just write this down here. Output shape of conv block 1, just so we get a little bit more information. And I'm just going to copy this, put it in here.
Let's just see. Why not? And we're gonna print the same here, but this time it's for on block 2. You know what? Let's also do the same for our classifier.
Here, that will become block 2.
Oh, look at that! Our viewer count is increasing. Hey to whoever to the people who just came in now.
And then finally, I want to know if
Yeah,
I
they
get an
used
output
to
shape
do
of
that around here.
classifier. So if I rerun all of this, I don't get an output shape of classifier. So my model is running into trouble once it gets to, so I get the output of conv block 1. I don't get an output of classifier. So this is telling me that I have an issue with my classifier layer. Now I know this because, well, I've coded this model before, and the in features here, we need a special calculation. So what is going on with our shapes? Mat1 and Mat2 shapes cannot be multiplied. So do you see here, what is the rule of matrix multiplication? The inner dimensions here have to match. We've got 490. Where did that number have come from? And we've got 10 times 10. Now, okay, I know I've set hidden units to 10, so maybe that's where that 10 came from. And what is the output layer or the output shape of conv block 2? So if we look, we've got the output shape of conv block 2. Where does that go? The output of conv block 2 goes into our classifier model, and then it gets flattened, so that's telling us something there. And then our NN linear layer is expecting
Output of con block 2 goes here and it flattens. In other words, 7 into 7. It becomes a tensor with 49 as one of its dimensions.
the output of the flattened layer as its in features. So this is where my trick comes into play. I pass the output of conv block 2 into the classifier layer. It gets flattened, and then that's what my NN linear layer is expecting. So what happens if we flatten this shape here?
It'll become 10 into...
Do we get this value? Let's have a look. So if we go 10
490,
times
yeah, that's
7
right.
times 7,
That's right.
490. Now, where was this 10? Well, that's our hidden units. And where were these 7s? Well, these 7s are the output of conv block 2. So that's my trick. I print the shapes of previous layers and see whether or not they line up with subsequent layers. So if we go times 7 times 7, we're going to have hidden units equals 10 times 7 times 7. Where do we get the 2 7s? Because that is the output shape of conv block 2. Do you see how this can be a little bit hard to calculate ahead of time? Now, you could calculate this by hand if you went into nconv2d, but I prefer to write code to calculate things for me. You can calculate that value by hand if you go through H out, W out. You can add together all of the different parameters and multiply them and divide them and whatnot, you can calculate the input and output shapes of your convolutional layers. You're more than welcome to try that out by hand, but I prefer to code it out. If in doubt, code it out. Now let's see what happens if we run our random image tensor through our model now. Do you think it will work? Well, let's find out. All we've done is we've added this little line here, times 7 times 7.
Oh, I see. I see.
And we calculate
Times 7 times 7.
that because we've gone, what if we pass a tensor of this dimension through a flattened layer? And what is our rule of matrix multiplication? The inner dimensions here must match. And why do we know that these are matrices? Well, mat1 and mat2 shapes cannot be multiplied. And we know that inside a linear layer is a matrix multiplication. So let's now give this a go. We'll see if it works. Oh, would you look at that? That is so exciting. We have the output shape.
Okay. That doesn't work. Okay, because I need to instantiate the model again. Where did I put that code? Yeah, there we go. So run this. Something's wrong here.
Shape of the... We'll see if it works. The inside a linear layer must match. And why do we know that these tensor of this dimension? All we've done is if we run our random image tensor through our model now, do you think it will work? Well, let's find out. All we've done is we've added this little line here, times 7 times 7. And we've calculated that because we've gone, what if we pass a tensor of this dimension through a flattened layer?
Mat1 and mat2 cannot be multiplied.
And what is our rule of matrix multiplication? The inner dimensions here must match. Why do we know that these...
Oh, okay. That one is this.
are matrices? Well, mat1 and mat2 shapes cannot be multiplied. And we know that inside a linear layer is a matrix multiplication. So let's now give this a go. We'll see if it works. Oh, would you look at that? That is so exciting. We have the output shape of the classifier is 1 and 10. We have, look, we have one number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. One number for each class in our dataset. Wow. Just like the CNN Explainer website. We have 10 outputs here. We just happen to have 10 classes as well. Now, this number again could be whatever you want. It could be 100, could be 30, could be 3, depending on how many classes you have. But we have just figured out
Where does
the
our
output
grade
shape
function say Adam though?
of each layer in our model.
Twist.
So that's very exciting. I think it's now time we pass a random tensor through. How about we pass some actual data through our model? In the next video,
Maybe
let's use our
it's
train and test step
something
functions
else.
to train our first convolutional neural network. I'll see you there. Let's get ready to train our first CNN. So what do we need? Where are we up to in the workflow? Well, we've built a model and we stepped through it. We know what's going on, but let's really see what's going on by training the CNN, or see if it trains, because we don't always know if it will, on our own data set, which is of fashion MNIST. So we're going to set up a loss function and optimizer for model 2. And just as we've done before, for model 2, turn that into Markdown. I'll just show you the workflow again. So this is what we're doing. We've got some inputs, we've got a numerical encoding, we've built this architecture, and hopefully it helps us learn, or helps us make a predictive model that we can input images, such as grayscale images of clothing, and predict. And if we look where we are at the Pytorch workflow, we've got our data ready. We've built our next model. Now here's where we're up to. Picking a loss function and an optimizer. So let's do that, hey? Loss function, or we can do evaluation metrics as well. So set up loss function / eval metrics / optimizer, and we want from helper functions import accuracy function. We don't need to re-import it, but we're going to do it anyway for completeness. Loss function equals nn.cross entropy loss, because we are working with a multi-class classification problem. And the optimizer we're going to keep the same as what we've used before, torch.optim SGD, and we'll pass it in this time. The params that we're trying to optimize are the parameters of model 2 parameters, and we'll use a learning rate of 0.1. We'll run that, and just to reiterate, here's what we're trying to optimize. Model 2 state tick. We have a lot of random weights in model 2. Have a look at all. All this. There's a bias, there's the weight. We're going to try and optimize these to help us predict on our fashion MNIST dataset. So without any further ado, let's in the next video go to the workflow. We're going to build our training loop, but thanks to us before, we've now got... Have a look at all this. There's a bias, there's the weight. We're going to try and optimize these to help us predict on our fashion MNIST dataset. So without any further ado, let's in the next video go to the workflow. We're going to build our training loop, but thanks to us before, we've now got functions to do this for us. So if you want to give this a go, use our train step and test step function to train model 2. Try that out, and we'll do it together in the next video.
I know we had waited this a long time back, so I'll just check the thing out again. For each batch, doing device agnostic code here, make a prediction, calculate the loss. We add the loss because just going to divide it by the batch, right? Yeah. Then same for the accuracy. Set optimizer to 0 grad, calculate loss backward, then optimize steps. Okay, I'm gonna sing the song now. Now, test step. Same thing, but we do it in entrance mode with the test data. And we don't need an optimizer.
We're getting so close to training our model. Let's write some code to train our first CNN model. Training and testing. Just going to make another heading here. Model 2, using our training and test functions. Woohoo! So we don't have to rewrite all of the steps in a training loop and a testing loop because we've already created that functionality before through our train step function. There we go. Performs a training, or this should be performs a training step with model trying to learn on data loader. So let's set this up. I'm going to set up torch manual seed 42, and we can set up a CUDA manual seed as well, just to try and make our experiments as reproducible as possible because we're going to be using CUDA. We're going to measure the time because we want to compare our models, not only their performance in evaluation metrics, but how long they take to train from time it. Because there's no point having a model that performs really, really well, but takes 10 times longer to train. Well, maybe there is, depending on what you're working on. Model 2 equals timer. And we're going to train and test the model. But the time is just something to be aware of, is that usually a better performing model will take longer to train. Not always the case, but just something to keep in mind. So for epoch, we're going to use TQDM to measure the progress. We're going to create a range of epochs. We're just going to train for 3 epochs, keeping our experiment short for now, just to see how they work. Epoch. And we're going to print a new line here. So for an epoch in a range, we're going to do the training step, which is our train step function. The model is going to be equal to model 2, which is our convolutional neural network, our tiny VGG. The data loader is just going to be equal to the train data loader, the same one we've used before. The loss function is going to be equal to the loss function that we've set up above, loss FN. The optimizer as well is going to be the optimizer, in our case, stochastic gradient descent. Optimizer equals optimizer. Then we set up the accuracy function, which is going to be equal to our accuracy function. And the device is going to be the target device. How easy was that? Now we do the same for the train, or the testing step, sorry. The model is going to be equal to model 2, and then the data loader is going to be the test data loader. And then the loss function is going to be our same loss function. And then we have no optimizer for this. We're just going to pass in the accuracy function here. And then, of course, the device is going to be equal to the device. And then, what do we do now? Well, we can measure the end time, so that we know.
Give me a second while I just write the code over here. Then we're gonna do the test step.
How long the code here took to run. So let's go train time end for model 2. This will be on the GPU, by the way, but this time it's using a convolutional neural network. And the total train time for model 2 is going to be equal to print train time, our function that we created before as well, to help us measure start and end time. So we're going to pass in train time start, model 2, and then end is going to be train time end, model 2. And then we're going to print out the device that it's using as well. So you ready? Are you ready to train our our first convolutional neural network. Hopefully this code works. We've created these functions before, so it should be all right. But if in doubt, code it out. If in doubt, run the code. Let's see what happens. Oh my goodness. Oh, of course. Oh, we forgot to comment out the output shapes. So we get a whole bunch of outputs for our model because what have we done? Back up here, we forgot to. So this means every time our data goes through the forward pass, it's going to be printing out the output shapes. So let's just comment out these. And
Alright, comment those out there.
I think this cell is going to take quite a long time to run because it's got so many printouts. Yeah, see? Streaming output truncated to the last 5,000 lines. So we're going to try and stop that. Okay, there we go. Beautiful. They actually work. Sometimes it doesn't stop so quickly. So we're going to rerun our fashion MSV2 model cell so that we comment out these print lines. And then we'll just rerun these cells down here. We'll just go back through. Fingers crossed there's no errors. And we'll train our
That out, did it?
model again. Beautiful. Not as many printouts this time. So here we go. Our first CNN is training. How do you think it'll go? Well,
Create a model again.
that's why we have printouts, right? So we can see the progress. So you can see here all the functions that are being called behind the scenes from Pytorch. So thank you to Pytorch for that. There's our train step function was in there. Train step, wonderful. Beautiful. So there's epoch 0. Oh, we get a pretty good test accuracy. How good is that? Test accuracy is climbing as well. Have we beaten our baseline? We're looking at about 14 seconds per epoch here. And then the final epoch, what do we finish at? Oh, 88.5. Wow, in 41.97979.
So with the CPU, this is gonna take some time, I guess. It took 44, was it? 41?
Seconds. Again,
41 seconds with the GPU for Daniel over there. But look at that, our viewer count is at 4. Hey to whoever came in just now. Put message in chat if you have any questions. What should we do? Should we switch to a GPU? I'll find it explaining something. That took 62 seconds for, yeah, Daniel wasn't kidding when he said CPU is slow for ML. I guess, you know what, let's just, yeah, we need a CPU this time. Let's see, so how do we change runtime? Let's switch to GPU. I guess that should do it. Should work now. Should work now. See, it's taking some time. It has to download this thing again, doesn't it? But I think it's still better than just waiting for CPU to complete the process. Would have taken way longer. Or alternatively, we can just set this to run on my own 4060 Ti, but yeah, that would take longer for me to set up. So let's just roll with this. Oops, so somewhere, what happened here? Name device is not defined. Let's just see whether it is good or now. Yeah, it is. Perfect. In that case, we'll come over here and instantiate the class again. Set our what's it? Well, import these functions. Yeah, Model 2 is not defined. There we go. Okay, let's set our loads and optimizer. And finally, we are gonna run our finger scroll now. What happened here? Train step is not defined. Hmm. What happened here? Where's our train step? We just need to rerun that cell again, don't I? Train step as well as test step. Those should be defined now, and we are gonna run our train our model on the GPU now. Fingers crossed this works. Oops, my camera is dead, isn't it? It sucks you can't see my reaction, but let me just plug this in. Alright, my phone is plugged in, and seems like our oops is finished. Oh, we have an
Your
88%
mileage may vary. Don't worry too much.
accuracy now. Oh, test accuracy is terrible.
These numbers aren't exactly the same on your screen, and
There's something's wrong with the test layer or something. Let's just see. Nothing with the test data loader, which would mean our test. Something's wrong with the test step function, perhaps. Accuracy should be with the data loader here. Hmm. Let's check out the code on the collab notebook. That's because why on that and read our define our model again. Is that version one? No, it's version two. To that, we need to set our to function optimizer and loss function now. And yep, now we run this and hopefully that yields a better result. something is wrong. Oh, we are not sending our. Yeah, this is why you need to do build device agnostic code. Okay, let's do this one last time. Hopefully, it's last time. Yeah. Now something is wrong. Hmm. You stupid child. Oh my god. It always turns out to be the most silliest typo, doesn't it? Okay. Uh,
And same with the training time, because we might be using slightly different hardware. What GPU do I have today? I have a Tesla P100 GPU. You might not have the same GPU. So the training time, if this training time is something like 10 times higher, you might want to look into what's going on. And if these values are like 10% lower or 10% higher, you might want to see what's going on with your code as well. But let's now calculate our Model 2 results. I think it is the best performing model that we have so far. Let's get a results dictionary. Model 2 results. This is so exciting. We're learning the power of convolutional neural networks. Model 2 results equals a val model. And this is a function that we've created before. So returns a dictionary containing the results of a model predicting on data loader. So now let's pass in the model, which will be our trained model 2, and then we'll pass in the data loader, which will be our test data loader. And then, oh, excuse me, typo. Our loss function will be, of course, our loss function, and the accuracy function will be accuracy function. And the device is already set, but we can reset it anyway. Device equals device. And we'll check out the model 2 results.
right. Let's see.
Make some predictions. Oh, look at that. Model accuracy, 88. Does that beat our baseline? Model 0 results. Oh, we did beat our baseline with a convolutional neural network. All right, so
Oh, I'm not sure if we have models or results, but yeah, it's not different. Anyway, I'm pretty sure it's better than zero.
I feel like that's quite exciting. But now let's keep going on and let's start to compare the results of all of our models. I'll see you in the next video. Welcome back. Now, in the last video, we trained our first convolutional neural network, and from the looks of things, it's improved upon our baseline. But let's make sure by comparing, this is another important part of machine learning experiments, is comparing the results across your experiments. So, and training time. Now, we've done it in a way where we've got 3 dictionaries here of our model 0 results, model 1 results, model 2 results. So, how about we create a data frame comparing them? So, let's import pandas as PD, and we're
Oh, I think it's the maybe not the first. Did we use pandas in this tutorial before? I don't remember. Anyhow,
going to compare results equals PD.dataframe. And because our model results dictionaries all have the same keys, let's pass them in as a list. So model 0 results, model 1 results, and model 2 results to compare them. Wonderful. And what it looks like when we compare the results. Alrighty. So recall our first
don't have model zero results and all.
Model was our baseline V0, which is 2 linear layers.
Yeah,
And so we have an accuracy of
basic.
83.4 and a loss of 0.47. The next model was we trained on the GPU and we introduced nonlinearities. So we actually found that that was worse off than our baseline. But then we brought in the big guns. We brought in the tiny VGG architecture from the CNN Explainer website and trained our first convolutional neural network. And we got the best results so far. But there's a lot more experiments that we could do. We could go back through our tiny VGG and we could increase the number of hidden units. Where do we create our model? Up here. We could increase this to say 30 and see what happens. That would be a good experiment to try. And if we found that nonlinearities didn't help with our second model, we could comment out the ReLU layers. We could, of course, change the kernel size, change the padding, change the max pool, a whole bunch of different things that we could try here. We could train it for longer, so maybe if we trained it for 10 epochs, it would perform better. But these are just things to keep in mind and try out. I'd encourage you to give them a go yourself. But for now, we've kept all experiments quite the same. How about we see the results we add in the training time, because that's another important thing that we've been tracking as well. So we'll add training time to results comparison. So the reason why we do this is because if this model is performing quite well, even compared to our CNN, so a difference in about 5% accuracy, maybe that's tolerable in the space that we're working. Except that this model might actually train and perform inference 10 times faster than this model. So that's just something to be aware of. It's called the performance speed trade-off. So let's add another column here, compare results, and we're going to add in, oh, excuse me, got a little error there, that's all right. Got trigger happy on the shift and enter. Training time equals, we're going to add in, we've got another list here, is going to be total train time for model 0, and total train time for model 1, and total train time for model 2. And then we have a look at our compare results dictionary, or sorry, compare results data frame. Wonderful. So we see, and now this is another thing I keep stressing this to keep in mind. If your numbers aren't exactly what I've got here, don't worry too much. Go back through the code and see if you've set up the random seeds correctly. You might need a CUDA random seed. We may have missed one of those. If your numbers are outlandishly different to these numbers, then you should go back through your code and see if there's something wrong. And again, the training time will be highly dependent on the compute environment you're using. So if you're running this notebook locally, you might get faster training times. If you're running it on a different GPU to what I have, NVIDIA SMI, you might get different training times. So I'm using a Tesla P100, which is quite a fast GPU, but that's because I'm paying for Colab Pro, which generally gives you faster GPUs. And Model 0 was trained on the CPU, so depending on what compute resource Google allocates to you with Google Colab, this number might vary here. So just keep that in mind. These values, training time, will be very dependent on the hardware you're using. But if your numbers are dramatically different, well, then you might want to change something in your code and see what's going on. And how about we finish this off with a graph? So let's go visualize our results. And doing this.
Let's see if my phone has enough charge now. Okay, turn on. Alright, let that turn on.
Have a look at the data frame above. Is the performance here, 10 seconds longer training time, worth that extra 5% of the result on the accuracy? Now, in our case, we're using a relatively toy problem. What I mean by toy problem is quite a simple data set to try and test this out. But in your practice, that may be worth doing if your model takes longer to train, but gets quite a bit better performance. It really depends on the problem you're working with. Compare results, and we're going to set the index as the model name, because I think that's what we want our graph to be. We want the model name, and then we're going to plot, we want to compare the model accuracies, and we want to plot the kind is going to be equal to bar H, horizontal bar chart. We're going to P, X label, we're going to get accuracy as a percentage.
I can't do this because I haven't defined Model 0 and V1, and the ones that even if they are defined, they are in CPU. So we'll just follow
And
through
we're
the
going to
video.
go P, Y label. This is just something that you could share if someone's asking, how did your modeling experiments go on Fashion MNIST? Well, here's what I've got. And then they ask you, well, what's the Fashion MNIST Model V2? You could say, that's a convolutional neural network that replicates the CNN Explainer website that trained on a GPU. They go, how long did that take to train? Well, then you've got the training time here. We could just do it as a vertical bar chart. I did it as horizontal so that this looks a bit funny to me. So horizontal like that. So the model names are over here. Wonderful. So now I feel like we've got a trained model. How about we make some visual predictions? Because we've just got numbers on a page here,
Yep,
but our model is trained on
finally.
computer vision data. And the whole point of making a machine learning model on computer vision data is to be able to visualize predictions. So let's give that a shot, eh? In the next video, we're going to use our best performing model, Fashion MNIST Model V2, to make predictions on random samples from the test data set. You might want to give that a shot. Make some predictions on random samples from the test data set and plot them out with their predictions as the title. So try that out. Otherwise, we'll do it together in the next video. In the last video, we compared our model's results. We tried 3 experiments. One was a basic linear model, one was a linear model with nonlinear activations, and Fashion MNIST Model V2 is a convolutional neural network. And we saw that from an accuracy perspective, our convolutional neural network performed the best. However, it had the longest training time. And I just want to exemplify the fact that the training time will vary depending on the hardware that you run on. We spoke about this in the last video. However, I took a break after finishing the last video, reran all of the cells that we've written, all of the code cells up here, by coming back to the notebook and going run all. And as you'll see, if you compare the training times here to the last video, we get some different values. Now, I'm not sure exactly what hardware Google Colab is using behind the scenes, but this is just something to keep in mind. At least for now on, we know how to track our different variables, such as how long our model takes to train and what its performance values are. But it's time to get visual, so let's create another heading. Make and evaluate. This is one of my favorite steps after training a machine learning model. So make and evaluate random predictions with the best model.
Yeah, it's the best
So
step.
we're going to follow the Data Explorer's motto of getting visual, or visualize. Let's make a function called make predictions. And it's going to take a model, which will be a torch nn.module type. It's also going to take some data, which can be a list. It'll also take a device type, which will be torch.device, and we'll set that by default to equal the default device that we've already set up. And so what we're going to do is create an empty list for prediction probabilities. Because what we'd like to do is just take random samples from the test data set, make predictions on them using our model, and then plot those predictions. We want to visualize them. And so we'll also turn our model into evaluation mode, because if you're making predictions with your model, you should turn on evaluation mode. We'll also switch on the inference mode. Also going to take some data, which can be a list. It'll also take a device type, which will be torch.device, and we'll set that by default to equal the default device that we've already set up. And so what we're going to do is create an empty list for prediction probabilities. Because what we'd like to do is just take random samples from the test data set, make predictions on them using our model, and then plot those predictions. We want to visualize them. And so we'll also turn our model into evaluation mode, because if you're making predictions with your model, you should turn on evaluation mode. We'll also switch on the inference mode context
Follow
manager,
best
because predictions is another word for
practice.
inference. And we're going to loop through for each sample in data. Let's prepare the sample. So this is going to take in a single image. So we will unsqueeze it because we need to add a batch size dimension on the sample. We'll set dim equals to 0, and then we'll pass that to the device. So add a batch dimension, that's with the unsqueeze, and pass to target device. That way our data and model are on the same device, and we can do a forward pass. Or we could actually up here go model.toDevice. That way we know that we've got device agnostic code there. Now let's do the forward pass. Forward pass, model outputs raw logits. So recall that if we have a linear layer at the end of our model, it outputs raw logits.
Right, doing device agnostic code here. Or writing device agnostic code here. I don't think we need to do this because of the newer Torch version, but
So pred logit for a single sample is going to equal model. We pass the sample to our target model, and then we're going to get the prediction probability. How do we get the prediction probability? So we want to go from logit to prediction probability. Well, if we're working with a multi-class classification problem, we're going to use the softmax activation function on our pred logit, and we're going to squeeze it so it gets rid of an extra dimension, and we're going to pass in dim equals 0. So that's going to give us our prediction probability for a given sample. Now,
and we're gonna take the max, aren't we?
now let's also turn our prediction probabilities into prediction labels. So get pred. Well, actually, I think we're just going to return the pred probs. Yeah, let's see what that looks like, because we've got an empty list up here for pred probs. So for matplotlib, we're going to have to use our data on the CPU. So let's make sure it's on the CPU, because matplotlib doesn't work with the GPU. So get pred prob off GPU for further calculations. So we'll just hard code it in here to make sure that our prediction probability is off the GPU. So pred probs, which is our list up here, we're going to append the pred prob that we just calculated, but we're going to put it on the CPU. And then let's go down here, and we're going to, so if we've done it right, we're going to have a list of prediction probabilities relating to particular samples. So we're going to stack the pred probs to turn list into a tensor. So this is only one way of doing things. There are many different ways that you can make predictions and visualize them. I'm just exemplifying one way. So we're going to torch stack, which is just going to say, hey, concatenate everything in the list to a single tensor. So, oh, we might need to tab that over. Tab, tab. Beautiful. So let's try this function in action and see what happens. I'm going to import random, and then I'm going to set the random seed to 42. And then I'm going to create test samples as an empty list, because we want a list of test samples to iterate through. And I'm going to create test labels also as an empty list, so that, remember, when we are evaluating predictions, we want to compare them to the ground truth. So we want to get some test samples, and then we want to get their actual labels, so that when our model makes predictions, we can compare them to their actual labels. So for sample, comma label, we're going to use random to sample the test data. Now note that this is not the test data loader. This is just test data. And we're going to set k equals to 9. And recall, if you want to have a look at test data, what do we do here? We can just go test data, which is our data set, not converted into a data loader yet. And then if we wanted to get the first 10 samples, can we
Alright, let me try to turn on my camera here. That worked. Yep, that worked. There we go. Alright, so let's
do that?
continue here.
Only one element tensor. Which is our data set, not converted into a data loader yet. And then if we wanted to get the first 10 samples, can we do that? Only one element tensors can be converted into Python scalar. So if we
What is sample? Sample and random Python. Returns a particular length list of items chosen from the sequence. That's a neat method. I didn't know.
get the first 0, then maybe we can go up. And then if we wanted to get the first test data, what do we do here? We can just go test data, which is our data set, not converted into a data loader yet. And then if we wanted to get the first 10 samples, can we do that? Only one element tensors can be converted into Python scalar, so if we get the first 0, then maybe we can go up to 10. Yeah, there we go. And what's the shape of this? Tuple has no object shape. Okay, so we need to go image label equals that, and then we check the shape of the image label. Oh, because the labels are going to be integers. Wonderful. So that's not the first 10 samples, but that's just what we get if we iterate through the test data. We get an image tensor, and we get an associated label. So that's what we're doing with this line here. We're just randomly sampling 9 samples, and this could be any number you want. I'm going to use 9 because this is a spoiler for later on. We're going to create a 3x3 plot, so that just 9 is just a fun number. So get some random samples from the test data set, and then we can go test samples.append sample, and we will go test labels.append label, and then
This is converting it into a neat list now.
let's go down here, view the first, maybe we go first sample shape. So test samples 0 dot shape. And then if we get test samples 0, we're going to get a tensor of image values. And then if we wanted to plot that, can we go plt imshow cmap equals gray, and we may have to squeeze this, I believe, to remove the batch tensor. Let's see what happens. Batch dimension. There we go. Beautiful. So that's to me a shoe, a high heel shoe of some sort. If we get the title, plt.title, test labels. Let's see what this looks like. It's a 5, which is, of course, class names. We will index on that. Sample. Okay, beautiful. So we have 9 random samples, 9 labels that are associated with that sample. Now let's make some predictions. So make predictions. And this is one of my favorite things to do, I can't stress it enough, is to randomly pick data samples from the test data set and predict on them and do it over and over and over again to see what the model is doing. So not only at the start of a problem, I'll just get the prediction probabilities here. We're going to call our make predictions function. So not only at the start of a problem should you become one with the data, even after you've trained a model, you'll want to further become one with the data, but this time become one with your model's predictions on the data and see what happens. So view the first 2 prediction probabilities list. So we're just using our make predictions function that we created before, passing it the model, the trained model 2, and we're passing it the data, which is the test samples, which is this list that we just created up here, which is comprised of random samples from the test data set. Wonderful. So let's go pred probs. Oh, we don't want to view them all. That's going to give us, oh, we want 2. The prediction probabilities for a given sample. And so how do we convert prediction probabilities into labels? Because if we have a look at test labels, if we're trying to compare apples to apples, when we're evaluating our model, we can't really necessarily compare the prediction probabilities straight to the test labels. So we need to convert these prediction probabilities into prediction labels. So how can we do that? Well, we can use argmax to take whichever value here, the index, in this case this one, the index of whichever value is the highest of these prediction probabilities. So let's see that in action. Convert prediction probabilities.
And all these numbers together would add up to what?
To labels. So we'll go pred classes equals pred probs, and we'll get the arg max across the first dimension. And now let's have a look at the pred classes. Wonderful. So are they in the same format? Format as our test labels? Yes, they are. So
See?
if you'd like to go ahead in the next
There we go. And if we do test labels,
video, we're going to plot these and compare them. So we're going to write some code to create a matplotlib plotting function that's going to plot 9 different samples along with their original labels and their predicted label. So give that a shot. We've just written some code here to make some predictions on random samples. If you'd like them to be truly random, you can comment out the seed here, but I've just kept the seed at 42 so that our random.sample selects the same samples on your end and on my end. So in the next video, let's plot these. Let's now continue following the Data Explorer's motto of visualize, visualize, visualize. We have some prediction classes. We have some labels we'd like to compare them to. You can compare them visually. It looks like our model is doing pretty good. But since we're making predictions on images, let's plot those images along with the predictions. So I'm going to write some code here to plot the predictions. I'm going to create a matplotlib figure. I'm going to set the fig size to 9 and 9 because we've got 9 random samples. You could, of course, change this to however many you want. I just found that a 3x3 plot works pretty good in practice. And I'm going to set n rows. So for my matplotlib plot, I want 3 rows and I want 3 columns. And so I'm going to enumerate through the samples in test samples. And then I'm going to create a subplot for each sample. So create a subplot, because this is going to create a subplot because it's within the loop. Each time it goes through a new sample, create a subplot of n rows and cols, and the index it's going to be on is going to be I plus 1, because it can't start at 0. So we just put I plus 1 in there. What's going on here? Enumerate. Oh.
Enumerate. So made a typo there.
Excuse me, in enumerate. Wonderful. So now we're going to plot the target image. We can go plot.inShow. We're going to get sample.squeeze, because we need to remove the batch dimension. And then we're going to set the CMAP is equal to grey. What's this telling me up here? Oh no, that's correct. Next, we're going to find the prediction label in text form, because we don't want it in a numeric form. We could do that, but we want to look at things visually with human readable language, such as Sandal for whatever class Sandal is, whatever number class that is. So we're going to set the pred label equals class names, and we're going to index using the pred class's I value. So right now we're going to plot our sample, we're going to find its prediction, and now we're going to get the truth label. So we also want this in text form. And what is the truth label going to be? Well, the truth label is we're going to have to index using class names and index on that using test labels I. So we're just matching up our indexes here. Finally, we're going to create a title for the plot. And now, here's what I like to do as well. If we're getting visual, well, we might as well get really visual, right? So I think we can change the color of the title text depending if the prediction is right or wrong. So we can create a title using an F string. Pred is going to be a pred label, and the truth label. We could even plot the prediction probabilities here if we wanted to. That might be an extension that you might want to try. And so here we're going to check
Truth label and pred label. Okay. Oops. That's gonna run.
for equality between pred and truth, and change color of title text. So what I mean by this, it's going to be a lot easier to explain if we just, if in doubt, code it out. So if the pred label equals the truth label, so they're equal, I want the plot.title to be the title text, but I want the font size, well, the font size can be the same, 10. I want the color to equal green. So if they're, so green text, if prediction, same as truth, and else, I'm going to set the plot title to have title text, font size equals 10, and the color is going to be red. So does that make sense? All we're doing is we're enumerating through our test samples that we got up here, test samples that we found randomly from the test dataset. And then each time we're creating a subplot, we're plotting our image, we're finding the prediction label by indexing
Font size, else we just make it red.
the class names with our pred classes value. We're getting the truth label, and we're creating a title for the plot that compares the pred label to the truth, and we're changing the color of the title text depending if the pred label is
Why did I code this 2 times?
correct or not. So let's see what happens. Did we get it right? Ooh, yes we did. Oh,
See, and all of them are right.
I'm going to do one more thing. I want to turn off the axes, just so we get more real estate.
Alright, let's do that.
I love these kind of plots. It helps that our model got all of these predictions right. So look at this. Pred,
One of them.
sandal, truth, sandal, pred, trouser. Truth trouser. So that's pretty darn good, right? See how, for me, I much prefer visualizing things. Numbers on a page look good, but there's nothing quite like visualizing your machine learning model's predictions, especially when it gets it right. So how about we select some different random samples up here? We could functionize this as well to do like all of this code in one hit, but that's all right. We'll be a bit hacky for now. So this is just going to randomly sample with no seed at all. So your samples might be different to mine.
That.
9 different samples. So this time we have an ankle boot. We'll make some predictions. We'll
Oh, okay, that's
just step through all of this code here.
maybe we just got very unlucky there. Let's get another sample and then run that.
Yeah.
Oh,
And
okay.
oh, there we go. It got one wrong. So all of these are correct. But this is more interesting as well, is where does your model get things wrong? So it predicted a dress, but this is a coat. Now, do you think that this could be potentially a dress? To me, I could see that as being a dress. So I kind of understand where the model's coming from there. Let's make some more random predictions. We might do 2 more of these before we move on to the next video. Oh, all correct. We're interested in getting some wrong here. So our model seems to be too good. All correct again. Okay, one more time. If we don't get any wrong, we're going on to the next video. But this is just really, oh, there we go, 2 wrong. Beautiful. So predicted a dress, and that's
Not beautiful actually. I am getting too many wrong here.
a shirt. Okay, I can kind of see where the model might have stuffed up there. It's a little bit long for a shirt for me, but I can still understand that would be a shirt. And this is a pullover, but the truth is a coat. So maybe there's some issues with the labels. And that's probably what you'll find in a lot of datasets, especially quite large ones. Just with the sheer law of large numbers, there may be some truth labels in your datasets that you work with that are wrong. And so that's why I like to compare the model's predictions versus the truth. On a bunch of random samples to go, you know what, is our model's results better or worse than they actually are? And that's what visualizing helps you do, is figure out, you know what, our model is actually, it says it's good on the accuracy, but when we visualize the predictions, it's not too good, and vice versa, right? So you can keep playing around with this, try
Either my model is very bad or maybe I'm just getting unlucky results. Okay, let's do one thing. Let's run the training loop again. Wait, what's happening? Something is definitely wrong here. Okay, stop that. Let's just go up and create a model again. And define our loads and optimize the function. Train the model again. Okay, that's more like it. Let that finish. Alright, and now we'll go ahead and this again. We are using model 2, right? I mean, we need to go and change this, don't we? Make predictions first and then plot this. You got most of them right. There we go. That looks way better. Alright.
Look at some more random samples.
I don't know what
Running this
happened
again,
there,
we'll
though, but it's
then we'll move on to the
fixed,
next video.
so
We'll
it
be able
is
to go on
what
to
it
another way. Oh, see, this is another example. Some labels here could be confusing. And speaking of confusing, well, that's going to be a spoiler for the next video. But you see how the prediction is a t-shirt top, but the truth is a shirt? To me, that
This looks like a shirt, but
label is kind of overlapping. Like, I don't know, what's the difference between a t-shirt and a shirt? So that's something that you'll find as you train models is maybe a model's going to tell you about your data as well. And so we hinted that this is going to be confused. The model is confused between t-shirt, top, and shirt. How about we plot a confusion matrix in the next video? I'll see you there. We're up to a very exciting point in evaluating our machine learning model, and that is visualizing, visualizing, visualizing. And we saw that in the previous video. Our model kind of gets a little bit confused, and in fact, I would personally get confused at the difference between t-shirt / top and a shirt. So these kind of insights into our model predictions can also give us insights into maybe some of our labels could be improved. And another way to check that.
alright, I think we'll continue in our next session. Yeah, I'll see you all tomorrow. I feel so good, doing this after these many days. But let's keep up this the excitement to learn. And yeah, I'll see you all in the next one. Till then, take care.